Okay, thanks to the session chairs for the kind introduction. My name is Sheng-Kai, come from the National Tsinghua University in Taiwan, and today I'm going to talk about my research related to the micro-tactile sensor. And this is the outline for today's presentation. Firstly, I'm going to talk about the background of the micro-tactile sensor, and secondly, I'm going to point out my motivation and the design concept of this study. And the next part is the fabrication process and results. And immediately following is the measurements and discussions. And the final part is the summary. So let's get started. Tactile sensor is known as a sensor which can capture the information of touching force. And there are various existed or promising applications of tactile sensor. And the tactile sensor is getting more and more attention years by years due to its versatile application needs. And in this summary table, we just simply categorize into 4 application fields. The first application field is in the automatic or robot-human communication in the robotic industry. And the second one is the analysis of the loading distribution and the safety collaboration in the engineering application field. And the third application field is in the medical devices. And the fourth application field is in the consumer product. Many cell phones nowadays will have the function of multi-stage button, which can analyze the force you apply on the screen or on the edge part of the cell phone. And due to the coming era of the Internet of Things, tactile information will become more and more critical and useful in the future. And this is the brief summary table of some available force sensor product. It can be divided into 3 parts due to different sensing mechanisms. And from the point of view of different fabrication process, to further taking the advantage of tactile sensor, the miniaturization is an essential approach to integrate more easily into your target system. So the MEMS technology is utilized for the needs of the high sensitivity and the high capacity reality. And from this summary table, only 3 of them are fabricated using the MEMS process. And the other feature that need to be emphasized is that they all need to be integrated with the micro-tactile bump to effectively apply the force. In addition, with the different applications, different design of the tactile sensor will play an important role corresponding to different using situations. So there are many researchers nowadays are focused on the design and the using situations of the tactile sensor. So I'm going to briefly summarize this issue, just in my opinion. So what is the common issue when using this kind of a micro-tactile sensor? The first one of the micro-tactile sensor is the special packaging and the wire bonding of the tactile sensor. The wire bonding and the special packaging will make the chip even bigger. As the pattern shown on the left slide, it shows assembly on the bump is not an easy task, and which require a very precise assembly process. And the second one is the contact interface problem. If the sensor doesn't have a force bump, you may have the risk of touching the bonding wire or not effectively apply the force. On the other hand, if you have the tactile bump integration with your tactile sensor, you can apply the force right on the sensor directly. And more importantly, the micro-tactile bump will restrict the loading to a specific area. And the third issue is the typical design of the capacitive sensing or the piezoresistive sensing, and the limitation of the thin film fabrication techniques. And because the electrorouting will cross the fixed end of the deformable membrane. So once the force is accidentally above the sensing range, the signal transmission may be interrupted. So let's get into the part of the motivation and design concept of this study. Due to the mentioned issue, we have implemented the inductive type tactile sensor with the integration of the tactile bump using the chrono ball from the previous study. And from the scheme, as you can see from these figures, it is composed of the chrono ball sensing interface, also which serves as a tactile bump at the same time, and the encapsulated polymer as a spring to deform. And the button CMOS sensing coil on a CMOS chip for the sensing core of the device. And the advantages of the inductive tactile sensor has several merits. The first one is the chrono ball acts as a tactile bump as well as the sensing interface at the same time. And it is a simple sensing scheme with the compatible CMOS process. And the most important thing is there's no fragile suspending thin film structures are required in these devices. And we also show the capability of the force sensing as the result shown in the right figures. Taking the different perspective of the coil sensing technology, the coil sensing technology can be usually divided into two sensing schemes. The first one is the inductance sensing using the one coil, while the others, which has already been implemented in the previous study. And the other one is the electromagnetic sensing using the two coils. One is for the excitation, while the others is for the sensing, and which has the other additional advantages like the tunable driving distance by different driving voltage, and the voltage sense signal output, and the sensing by integration with the sensing interface, or you can use the sensing by two-coil gap change. And in this study, we want to use the cross-stable sensing interface integration, so we will use the sensing by integration with the sensing interface instead of the sensing by two-coil gap change. And I'm going to introduce the design concept of this study. And this is the schematic structure of the previous study. And using the one single sensing coil of the CMOS chip. So when the sensing distance between the sensing object is approaching the sensing coil, the inductance will vary. So let's put the other driving coil underneath and apply the AC signal into the excitation coil. At the same time, the induced AC voltage will also form in the sensing coil. Similar to the previous tactile sensing, the distance between the sensing object is approaching the sensing coil, then the induced voltage will also change. Hence, we can analyze the normal loading we applied on the device. And this slide shows the sensing principle, and the whole picture will be more clear. And this is the Ganford chart. After driving the PCB coil with an AC signal, a corresponding AC magnetic field and induced voltage with an initial induced voltage V0 will be introduced to the sensing coil of the CMOS chip. As the external loading applied on the cross-steel ball, the polymer will be deformed. So the distance between the cross-steel ball and the sensing coil will change. So the induced AC magnetic field and the induced voltage will also vary. So according to the variation of the induced voltage, the tactile force applied on the sensor can be extracted. So let's get into the part of the fabrication process and the result of the device. And this is the multi-layer staking by the TSMC 0.1 M1 poly-6 metal standard CMOS process. And the first step, we use the metal wet etching to define using the sulfuric acid and the hydrogen peroxide. And the bonding pad and the sensing coil are protected by the upper dielectric film. And the next step, we use the reactive ion etching to open the bonding pad. And then we wire bonding the electrical pad for the electrical connection and protect the bonding wire by epoxy. Then the CMOS chip was then encapsulated by the polymer using the polymer molding. And finally, after the adhesion of the cross-steel ball using the polymer, the molded CMOS chip was then bonded on the PCB with the coil. And this device is consisted of the cross-steel ball loading interface, the encapsulated polymers, the spring, and the sensing coil chip on the CMOS chip. And this is the driving coil underneath. So the reason why we use the cross-steel ball as a tactile interface is that it is an existing component used in the traditional industry. And the second one is it has the magnetic permeability. As you can see, it is attached by the magnets. And the more important thing is the dimension is compatible with our micro-tactile sensor. And this is the CMOS chip, and with the sensing coil and the other test key. And this is the encapsulated device after the polymer encapsulation. And from this picture, you can see the loading interface and the polymer and the CMOS chip, and the bonding wire is protected by the epoxy. So let's get into the part of the measurement and discussions. The measurement can be divided into two parts. The first one is the electrical test, and while the others is the force test. And I will introduce the electrical test first. But before that, let me introduce the testing system of the measurement setup. The function generator is applying the AC signal into the driving coil, and the signal of the sensing coil is connected to the oscilloscope, and the sensor is loading by the flat loading probe. Meanwhile, the sensor is fixed on the position stage, combining with the commercial force gauge. So once we apply positioning on the Z direction, a corresponding tactile force will be applied on the devices. So let's take a look at the electrical test first. And the x-axis is the driving frequency, while the y-axis is the induced voltage of the device. And this result indicates the sensing signal may vary with the driving voltage and frequency. To avoid the variation of the sensing signal induced by the fluctuation of the driving frequency, a relatively flat frequency response region, 9 MHz, is selected for the following test. And this result shows the difference before and after the integration of the chrome steel ball. The device with the integration of the chrome steel ball shows higher induced voltage. Besides, the higher of the driving voltage we apply, the higher of sensing voltage we can have. And after the confirm of the electrical signal, we measure the loading response of the devices. And this is the measurement result of the sensor before and after the integration with the chrome steel ball. The tactile sensor with the chrome steel ball integration have the sensitivity of 0.53 millivolt per Newton within the loading range of 0 to 2.4 Newton, and the driving voltage is 5 volts. Moreover, no signal is detected on the device without the integration of the chrome steel ball, which verify the sensing scheme of the proposed method. And note that there's no damage of the polymer within the loading range and no initial signal shift of each cycle, but more investigation of the polymer is still required in the future. And this result also indicates the important conclusion that the chrome steel ball not only acts as a force interface, but also enables the signal change of the tactile sensor. Since the polymer is a critical and inevitable component frequently used in the tactile sensor, we also categorize the force response when increasing and decreasing the loadings. And the variation between two response curve is mainly due to the hysteresis effect of the polymer, and which should be taken into concern for the future system signal processing. And this measurement depicts the sensing voltage and sensitivity can be further modified and tuned by the change in the driving voltage depends on the needs of the application. In other words, if the initial distance between the driving and the sensing coil is different in your application, you can compensate by tuning the driving voltage, which offers more flexibility in the system integration. So let's get into the final part of the presentation, summary. So this work proposed and demonstrated concept for the wireless electromagnetic tactile sensing. The presented design has no gap change between the sensing coil and the driving coil. The induced voltage change is mainly resulted from the displacement of the chrome steel ball. And the output signal and sensitivity can be further tuned by changing the driving voltage. And this is the acknowledgement. I want to thank the TSMC and CIC for providing the platform. I want to thank the CMMM of National Tsinghua University, Taiwan for providing the fabrication facilities. Finally, I thank the Ministry of Science and Technology of Taiwan for providing the research funding. So this is the end of the presentation. Thank you for your attention.